Changing a furnace heater connection from delta to Y requires careful evaluation and may not address the core problem. Firstly, conductor capacity must be sufficient. Changing to a Y configuration necessitates a neutral conductor. Attempting to add a 500 mcm neutral conductor to the existing 3-inch pipe is likely not feasible because of space limitations and the presence of bends in the conduit run. The conduit may be completely full. Secondly, potential safety hazards exist. Pulling all 4 cables, the 3 phases, and the existing neutral, if there is one, out of the pipe to accommodate a new neutral conductor introduces a significant safety risk. Disturbing the existing wiring could lead to electrical shorts or other malfunctions, especially given the age and potential degradation of the insulation. Thirdly, changing the wiring configuration from delta to Y is unlikely to solve the fundamental problem. The root cause of the heater blowouts and subsequent zone damage needs to be identified and addressed directly. Instead of focusing solely on the delta to Y conversion, a thorough investigation should be conducted to pinpoint the actual cause of the failures. Consider factors such as circuit overloading, faulty equipment, which could include the heaters themselves or the control system, or improper maintenance procedures. Finally, alternative solutions may offer a more effective and safer approach. Firstly, consider upgrading the existing circuit with larger gauge conductors. If the current 500 mcm conductors are insufficient for the load, replacing them with larger conductors or adding parallel circuits can increase the system's capacity and reduce the risk of overloading. Consult the National Electrical Code, NEC, Table 310.15. B16 or the appropriate table for your specific situation to determine the correct conductor size for the anticipated load and installation conditions. Secondly, consider installing surge protectors or other electrical safeguards. Surge protectors can help protect the heaters and associated equipment from voltage spikes and transients, which can contribute to premature failure. These devices should be installed at the service entrance and at the equipment itself to provide comprehensive protection. Thirdly, a comprehensive maintenance and inspection program is critical. Regular inspections and maintenance can help identify and address potential problems before they lead to failures. This program should include checking the condition of the wiring, connections, and equipment, as well as testing the operation of the heaters and control systems. It is very important to conduct a thorough analysis of the situation, including a risk assessment, before making any significant changes to the electrical system. This analysis should evaluate the potential risks and benefits of each proposed solution, as well as the impact on the overall system. Ensure that the solution that is chosen addresses the root cause of the problem and does not introduce new safety hazards. Delta and Y configurations are 2 common ways to connect 3-phase electrical loads. In a delta connection, the 3 phases are connected in a closed loop, forming a triangle. There is no neutral connection in a pure delta system. In a Y connection, the 3 phases are connected to a common neutral point, forming a Y shape. Understanding the differences between these configurations is essential for troubleshooting and modifying electrical systems. A delta connection is often used in applications where a high starting torque is required, such as motors. It provides a higher voltage to the motor windings during startup, which results in increased torque. However, a delta connection can also be more susceptible to voltage imbalances and harmonics, which can lead to equipment damage. A Y connection is generally preferred for systems where a neutral connection is required for single-phase loads or for grounding purposes. It provides a more stable voltage and is less susceptible to voltage imbalances. However, a Y connection may not provide as high a starting torque as a delta connection. When considering a delta to Y conversion, it is essential to understand the impact on voltage and current levels. In a delta connection, the line voltage is equal to the phase voltage, while the line current is equal to the square root of 3, approximately 1.732 times the phase current. In a Y connection, the line voltage is equal to the square root of 3, approximately 1.732 times the phase voltage, while the line current is equal to the phase current. This means that converting from delta to Y will typically result in a low phase voltage and a higher phase current. This change in voltage and current levels can affect the performance of the heaters and other equipment connected to the system. It is important to ensure that the equipment is compatible with the new voltage and current levels before making the conversion. The existing 3-inch conduit may not be large enough to accommodate the additional neutral conductor required for a Y connection. The NEC specifies the maximum number of conductors that can be installed in a conduit of a given size based on the conductor size and insulation type. Refer to NEC Chapter 9, Table 1 for conduit fill requirements. Exceeding the conduit fill limits can make it difficult to pull the conductors, damage the insulation, and reduce the ampacity of the conductors. If the existing conduit is not large enough, it may be necessary to install a new, larger conduit to accommodate the additional conductor. Pulling conductors through a conduit with multiple bends can be challenging. The NEC specifies the maximum number of bends allowed in a conduit run between pull points, which is typically 360 degrees. Exceeding this limit can make it difficult to pull the conductors and damage the insulation. If the existing conduit run has too many bends, it may be necessary to install additional pull boxes or junction boxes to reduce the number of bends between pull points. The age and condition of the existing wiring should also be considered. If the wiring is old or damaged, it may be more susceptible to failure when disturbed during the delta to Y conversion. In this case, it may be necessary to replace the wiring entirely to ensure the reliability of the system. The National Electrical Code (NEC) provides detailed requirements for the installation and maintenance of electrical systems. It is important to consult the NEC and other applicable codes and standards to ensure that the delta to Y conversion is performed safely and in accordance with all applicable regulations. The NEC covers topics such as conductor sizing, overcurrent protection, grounding, and wiring methods. Failure to comply with the NEC can result in electrical hazards, equipment damage, and legal liabilities. Consider performing an electrical load calculation to determine the actual load on the circuit. This calculation should take into account all of the heaters and other equipment connected to the circuit, as well as any future load additions. The load calculation will help determine the correct conductor size and overcurrent protection for the circuit. If the load calculation reveals that the circuit is overloaded, it may be necessary to reduce the load, upgrade the conductors, or add additional circuits. The heaters themselves may be faulty or improperly sized for the application. Check the heater specifications to ensure that they are compatible with the voltage and current levels of the system. Also, check the heater elements for signs of damage, such as cracks, breaks, or corrosion. If the heaters are faulty, they should be replaced with new heaters that are properly sized for the application. Improper maintenance practices can also contribute to heater failures. Ensure that the heaters are regularly cleaned and inspected, and that any necessary repairs are performed promptly. Also, ensure that the control system is functioning properly and that the heaters are not being overstressed due to improper control settings. Surge protection is a critical component of any electrical system, especially those that are susceptible to voltage spikes and transients. Surge protectors work by diverting excess voltage away from sensitive equipment, protecting it from damage. Surge protectors should be installed at the service entrance and at the equipment itself to provide comprehensive protection. There are several types of surge protectors available, including metal oxide varistors, MOSFETs, silicon avalanche diodes, and gas discharge tubes. The type of surge protector that is best suited for a particular application will depend on the voltage and current levels of the system, as well as the type of equipment being protected. A comprehensive maintenance and inspection program is essential for ensuring the reliability and safety of any electrical system. This program should include regular inspections of the wiring, connections, and equipment, as well as testing of the operation of the heaters and control systems. The maintenance and inspection program should be documented, and any findings should be addressed promptly. The program should also include training for personnel on proper maintenance procedures and safety precautions. The electrical system should be properly grounded to provide a safe path for fault currents. Grounding helps to protect personnel from electrical shock and prevents equipment damage. The grounding system should be inspected regularly to ensure that it is functioning properly. The grounding system should comply with the requirements of the NEC. If the existing wiring is old or damaged, it may be necessary to replace it entirely to ensure the reliability of the system. The new wiring should be sized in accordance with the NEC and should be installed by a qualified electrician. The new wiring should also be properly supported and protected from physical damage. Consider using a power quality analyzer to monitor the voltage, current, and harmonics in the electrical system. This analyzer can help identify potential problems such as voltage imbalances, harmonic distortion, and transient voltage spikes. The data from the power quality analyzer can be used to diagnose problems and to optimize the performance of the electrical system. Consult with a qualified electrical engineer to evaluate the electrical system and to recommend the best course of action. An electrical engineer can perform a thorough analysis of the system, including load calculations, voltage drop calculations, and short circuit studies. The electrical engineer can also help to identify potential problems and to recommend solutions that are safe, reliable, and cost-effective. Consider the use of energy-efficient heaters. Energy-efficient heaters can save energy and reduce operating costs. There are several types of energy-efficient heaters available, including infrared heaters, ceramic heaters, and heat pumps. The type of energy-efficient heater that is best suited for a particular application will depend on the heating requirements and the operating conditions. Consider the use of a programmable logic controller, PLC, to control the heaters. A PLC can be used to precisely control the temperature and to optimize the energy consumption of the heaters. A PLC can also be used to monitor the performance of the heaters and to detect any problems. The use of a PLC can improve the efficiency, reliability, and safety of the heating system. Ensure that all electrical work is performed by a qualified electrician. A qualified electrician has the knowledge, skills, and experience to perform electrical work safely and in accordance with all applicable codes and standards. Using a qualified electrician will help to ensure that the electrical system is safe, reliable, and code compliant. Document all changes made to the electrical system. This documentation should include a description of the changes, the date the changes were made, and the name of the person who made the changes. This documentation will be helpful for future maintenance and troubleshooting. The documentation should be kept in a safe place and should be readily accessible. Regularly review the electrical system to ensure that it is operating safely and efficiently. This review should include a visual inspection of the wiring, connections, and equipment, as well as a review of the maintenance records. The review should be performed by a qualified electrician or electrical engineer. The furnace heater failures that keep blowing out the heaters may not be electrical in nature. It is very likely these failures are caused by excessive temperatures inside the furnace or other environmental conditions. Therefore, even if you proceed to install a Y, the problem will persist.